I'd like to welcome Andrew Ireland. It's apparently midnight his time now, so he should be real sharp, as usual. He's going to tell us about software verification.
Thanks, John. So today I'm going to be talking about a proposal that's very new, or a project that's very new. It's really in the proposal form. We're just taking forward now. It's about 4 months old. The focus, as John said, is on software verification, in particular automatic software verification. So what I intend to do in this presentation is really to give you some motivations, explain the foundations for the project, and also headline the approach we're taking. So it's going to be at quite a high level, but I'm going to use examples to motivate what we're doing. Okay, so first off, the cornerstone of this project is a new logic. This is not of our own design. This is a logic that we're building upon called separation logic. And separation logic is only maybe about 7, 8 years old. It's an extension to the standard Hoare logic for programming. So I'll go into a bit of the background of that. And then I'm going to then focus in on the automatic software verification challenges. So my background is very much in automated reasoning. So I'm interested in applying automated reasoning techniques to new logics, and in particular, logics that can be used for developing correct programs. And in particular, I'm going to focus on this notion of cooperation that's in the title and is where the core of the core project comes from. And I'll come back to that at the end after I've gone through my examples to show what I mean by cooperation here, more than just simple integration. So a few more project details. So my postdoc, Ian McLean, and my PhD student, Anthony Hind, are already working on this project back in Edinburgh. It's supported by the British government through EPSRC, and there's a website so you can find more information, background papers, and presentations. So to start off, separation logic. As I said, it's a very new logic. It was designed as a joint effort between John Reynolds from CMU and Peter O'Hearn from Queen Mary University in London. As I said, it extends Hoare's as axiomatic approach to programming. Essentially, it introduces new assertions that allow you to talk about the heap. And it was created to allow one to reason about pointer-based programs. These are very widely used, but notoriously hard to prove correct and maintain those proofs. And separation logic has a real advantage when doing those kinds of proofs, and we want to build on that advantage. For example, it's able to deal with dirty features like memory disposal and address arithmetic in a very elegant way. The central selling point of separation logic, though, is a notion which is called local reasoning. That is, in order to reason about a program, the idea is that you should only have to worry about the parts of the heap which it touches. Okay, so to show this graphically, I've got a program on the left here, and this is the big yellow heap on the right. So if we're interested in reasoning about the correctness of this central piece, let's say it's a subroutine, then ideally we only want to talk about or think about or worry about the subpart of the heap, the heaplet, for which that program unit can actually touch. Okay? And this is what separation logic provides you with. At the logical level, that's done by introducing what's called the separating conjunction. Okay? So the separating conjunction operator is this star here. So if we assert P star Q, what we're saying is that we can divide the heap. We can separate it into two disjoint chunks, one of which, this red one here, for which the P is true, one of which here is green, for which Q is true. Okay, so it's a spatial operator, logical operator. So I'm going to run through a little example, execute a little program to give you a flavor of how the program relates to the logic, or vice versa. So the top here is the store, below the line is the heap. The first instruction is our allocation, represented here by a cons. So we're allocating two adjacent cells of the heap, and we're initializing them to 1 and 2. So that's represented here in the picture. So X points to the first element, and it has this adjoining cell next to it. This is represented in separation logic by the maps to operator. X maps to the pair of adjacent heap cells containing 1 and 2. Too quick there. The second command here is allocating another 2 cells, 3 and 4, pointed to by Y. Okay? In separation logic, because we can separate these 2 heaplets, at this point our heap is containing just 4 cells. So we can separate them into 2 pairs, and that's represented using the separation connective I introduced on the previous slide. Okay, now we can mutate the heap elements. So here square brackets is dereferencing. So what we're doing is we're taking the contents, excuse me, of what X plus 1 points to and reassigning that to what Y points to. So we're introducing a pointer from the second cell on the left to the first cell on the right of the pair. And in the last step, we're taking the 4 and we're reassigning that cell so that it points to the first element. Okay, so you can see the separation logic assertion has now changed. We have Y here where we had 2 before, and we have X here where we had 4 before. Okay? So a cornerstone of the logic, not surprisingly, is the frame rule. This is the rule which, linked with the separating conjunction operator, allows us to get this local reasoning. It allows us to decompose larger specifications and programs into smaller specifications and programs. Okay, so if we think about using this rule in backwards direction, as we're moving back, we have a frame invariant, a frame axiom corresponding to R, and we're able to isolate just those parts of the specification below which are relevant to verifying the code C in the middle here using these Hoare triples. Okay, so a key side condition is that R, this invariant here, none of the variables occurring in that are modified by C. If we preserve that, then this is a sound rule of inference. So moving forward, it's like building up verifications of small program fragments, and then this rule allows you to join them together. Okay, so separation logic, just to recap, is this new logic. It extends Hoare, classic Hoare programming logic, and its great virtue is that it allows this local style of reasoning, and that local style of reasoning gives the promise of scalable reasoning when it comes to reasoning about pointer programs. So my interest is in, as I said before, the automated reasoning, the automated reasoning, the theorem proving in particular, that you would need in order to make this framework, this logic, mechanical or automatable. So I'm going to tell you now about some of the challenges that our project is going to focus on in the next 3 years. And we've made some progress already. I'll refer back to at the end. I'm going to do that by a few examples, and I'm going to base those examples around an acyclic linked list data structure. Okay, so we have a head pointer here, I, and the tail is delimited here by j. The top elements represent content or data, A1 through to AN. So this pictorial representation is represented below by this predicate list. Now this list predicate has 3 arguments. The first argument is an abstraction of the linked list structure. It's simply abstracting out the data values. So this represents the picture above, So the data values are A1, A2 through to AN. That's represented here using a prolog list notation. So think of that as a sequence of data elements. The second two arguments relate this abstract view of a data structure to the actual pointer level data structure. So that's modeled here by a pointer to the first element in the data structure, I, and a pointer to the last element in the data structure. So you can think of this data structure as representing a segment of a linked list structure. So typically the ones we will look at, this J here will be nil. They'll be terminating segments. Above here is the inductive definition for the list predicate I've described informally below. So the top case is the base case. When we're dealing with the empty list, the list containing no data, then that means that we're looking at the empty heap. Okay? And that means that the pointers y and z must be equivalent at that point. This is the recursive case, the step case, if you like. We're looking at the constructed element here, again using a prolog notation. W is the head, X is the tail of the data component. If we are to unfold that, we introduce the separating logic conjunction again. So on the left here, we have the top element. So Y, the outer pointer, is pointing to a pair. W is the head of the list, and P is a pointer represented here by the existential quantifier P, which links the head of the list to the tail of the list. Okay, so you can think of these existentials as providing ways of talking about internal pointers. Okay, so we're going to use this definition a few times now. So the first challenge, if you want to automate verification efforts in this logic, reasoning about pointer programs, is you've got to invent these frame axioms. So this simple example here is a copy list example. So the precondition at the top here is that I points to a list with contents A, terminating in nil. The postcondition we're going to verify against is at the end of the computation that I still points to a list with contents A, but there's a separate list now pointed to by J, which also has the contents. Its value is the same. So we now have two copies of the same list. And this is the algorithm. I won't go into too much detail. It's recursive is the main point to take away. And when we make the recursive call here on the tail of I and the tail of J, then we get to assume our specification at the call point. Okay? It's analogous to the induction hypothesis, if you think in terms of recursion and induction. The eureka step we're looking for, though, is this R here. So this is a meta variable in this presentation. It's a gap. We've got to fill that in. If we can't fill that in, then we can't complete the proof. And in this particular example, I've filled in what that red meta variable should be instantiated to. It's this structure here. So I won't go into the details, but this separation logic conjunct is essentially talking about the rest of the heap at the level above the recursive call of the procedure. Okay? And if you think about this in even more detail, you can actually isolate parts of this missing information. Some of it's talking about the shape of the heap in this missing R, and some of it's talking about the content. Okay? And I'll keep coming back to this idea that these specifications, but also this missing information can be decomposed into content and shape. And we're going to use that in the way in which we tackle the automated reasoning problem. Okay, so the second example is an iterative example. So going from recursion to iteration, we're reversing a list here. So the specification at the top we have a list again, I, list with head pointer I, content A. We give the content A a name, A init, the initial value of A. And at the very end of the computation, at the end of the loop, then we've got another list pointed to by J with content B, such that B is equal to the reverse of A init. Okay, so we've started with a list pointed to by I. We've got a list pointed to by J at the end. And the contents of that J list is the reverse of the A list. So we've accomplished the list reversal task. Now the Eureka step here, not surprisingly, is coming up with a loop invariant. Okay, coming up with essentially the work that remains to be done and the work that has been achieved so far, the partial result, if you like. And again, there's two parts to this. There's the shape part, which basically tells us that there's a list still pointed to by I and a list pointed to by J. So we're building up this result list B while we're going through the list A. There's also a content part. It's a sort of functional part. It's telling us that at an arbitrary step in the loop, then if we append the reverse of A to B, that's the contents of the list pointed to by I and the contents of the list pointed to by J, if we reverse the A and glue it, append it onto the front of the B, then that will be the reverse of the initial list, A init. Okay? So eventually this A will dissolve away, it will become nil, and we'll be left with B here when we get to the post condition. Okay? So we've got to invent this structure in order again for the proof to go through. So the last application I'm going to look at, or the last challenge, is that quite often when we're doing verifications at this level, it's not enough just to have the definitions. We need to have additional lemmata, additional properties that allow the proof to go through. And in particular, we very often need inductive properties. So this last example is about Lammer Discovery. The program is simply taking two lists, one containing A, one containing B. The list containing A is pointed to by X. The list containing B is pointed to by Y. And what we want to do is to get a list pointed to by X with content C, such that C is equal to A appended to B. Okay, so this is just a functional presentation of this iterative structure here. And the key thing you need to do here is you need to invent a lemma, an inductive lemma, which allows you to reason about this gluing together of two list data structures, essentially. And that's the inductive lemma there. Taking the list pointed to by the, terminating in W, and then gluing that onto the list W, terminating in nil, is equivalent to just the list starting with the, ending in nil, with contents X appended to Y. So this again is a Eureka step in verifying that program. So we're interested in automating all of these types of Eureka step. And again, there's a shape component, and again, there's a content component to coming up with these structures. Okay, so I'm now going to move towards the end of the talk, so I'm going to talk about the approach we're taking. So what we're going to do is we're picking up separation logic, but we're also picking up some off-the-shelf tools. In particular, a tool called Smallfoot, which comes out of Peter O'Hearn's group in London. Smallfoot is essentially a shape analysis tool which is based upon symbolic execution of a program where the heap is specified using separation logic. So Smallfoot was developed so it would operate on loop 3 code. That is, you would have to provide loop invariants for the verifications to go through. An extension of Smallfoot, RG, for rely guarantee, developed by Matthew Parkinson at Cambridge, has been developed for working with Java applications. One of its features is that it deals with shape invariance by using a process of abstraction to generate the shape invariance I just talked about 2 slides ago. Okay? But we are interested in both shape and content. So we want to use these tools, and one of the things we want to do is to make these tools extensible. Okay? Currently, the tools are hardwired for certain data types, acyclic lists, binary trees, etc. If you need to introduce a new data type, then you would have to prove a lot of theorems, create additional inductive lemmas. So we want to support that activity. That's where our expertise comes in. The other part of the mix in terms of this project is the area where we come from, and that is automatic theorem proving, and in particular a technique called proof planning. So proof planning was invented by Alan Bundy at Edinburgh University in the late 80s, and it's been developed ever since and applied on a number of projects now. So the basic idea behind proof planning, or the best way I think to describe it is think of proof plans as kind of design patterns, or they are analogous to what design patterns would be when you're capturing common patterns of reasoning at a high level. And the idea is that if you have common patterns of reasoning represented in this kind of planning framework through what are called methods and critics, you can use those common patterns to constrain the search, that is, automate the search for proofs. So proof planning is a hierarchical activity. You have various levels of proof plans. So you start with your conjecture and your theory, and there is feedback here because you may modify your conjecture, generalize it. You may modify your theory, discover lemmas. And as you work down, you generate what's called a tactic. So a tactic is simply a program. It's a very low-level part of the proof process. It guides a proof checker in making sure that the proof that's come from the proof planner is indeed sound. So proof planning itself is not sound. Its focus is on search and automating search. We rely upon a proof checker to make sure that the proof plan as instantiated is indeed gives us a proof. So this kind of pulling these activities apart, proof planning and proof checking, gives us the ability to reuse high-level strategies, proof plans, gives us robustness because we can do analysis which allows us to do things like generalization and lemma discovery. And it also has been shown to facilitate integration because we can communicate between various systems at the planning level much easier than at the proof checking level. So one of the key features of proof planning we're going to make use of is middle-out reasoning, where we use meta variables to delay the choice. So there was 3 examples I showed you. The areas of choice we're focusing on are the axiom, the frame axiom I showed you, the loop invariance, and also just working out missing lemmas requires middle-out reasoning. I didn't quite show you that detail. So this kind of middle-out reasoning is facilitated by what are called proof critics. So critics, if you think of proof plans and methods as design patterns, proof critics are like anti-patterns. They capture common patterns of failure, and along with those common patterns of failure, they associate patches, ways in which you can get around the failure in the proof. In much the same way as we, in attempting to do a proof, will realize we need a missing lemma, or the conjecture we need to prove needs to be generalized. So we have quite a lot of experience of using this mechanism in generalizing conjectures, coming up with lemmas, and also loop invariants from previous projects. In terms of cooperative reasoning, previous projects where Cambridge Hall was linked to the CLAM proof planner at that time, and that was used to bring mathematical induction or automatic search for mathematical induction proofs into the Hall system. Most recently, I worked with a company called Praxis, where we developed a tool called SPADE-EASE, which applied proof planning and lightweight program analysis to the Spark language. This is the Ada subset that Colin was talking about this morning. And there we were automatically generating loop invariants for exception freedom proofs. So lastly, I want to come back to this cooperative reasoning. I put it in the title for good reason, because it is a central theme of the project. So one way you can think about a cooperation is that it's just the sum of the two parts. You have this part here and this part here. You glue them together, and what you have is just the sum of the parts. Well, we believe that we can achieve some synergies and get more than just the sum of the two parts. And the difference is, instead of just gluing things together, adding them together, we're looking for interaction between the two parts. And in particular, we're looking for interaction where the complementary techniques compensate for each other's weaknesses. So both of the techniques I've talked about, proof planning and symbolic execution through the Smallfoot family of tools, have their strengths, but they also have their weaknesses. And we want to compensate for those weaknesses by drawing upon the other tool. And we believe by doing that, the outcome will be larger than the individual components on their own. So what do I mean by that? Well, in terms of symbolic execution and Smallfoot, shape invariance is something which is not well suited, or shape invariance discovery is not well suited to the proof planning approach. The proof planning approach relies quite heavily on syntax. There's less syntax involved in these shape properties for our proof plans to be able to constrain the search for appropriate invariants. On the proof planning side, we can deal with content. Smallfoot doesn't deal with content at all, it's just this shape. Whereas the content is definitely a theorem-proving activity. So the proof planning has a powerful contribution to make there. There's also soundness. So I should add that the Smallfoot tools are sound, okay? But if you were to extend the tools, or if we moved outside the Smallfoot family of tools to other tools which we treated just purely as oracles, we could use the information that they pass across and not care about the soundness, because ultimately the proof planner, coupled with a proof checker, will give us the soundness guarantees. So it kind of liberates the kind of integrations we can go for. We can talk to things like shape analysis, but we could also talk to much more liberal tools where there is no soundness proof lying behind them. And also extensibility. I mentioned this earlier. If we want to extend the Smallfoot family of tools based around symbolic execution, then we have to come up with new inductive lemmas. That's precisely what the proof planning framework has a proven track record in. So, the executive summary. So the key observation is that these specifications can be broken down into shape and content. And we're exploiting that. We're using shape analysis tools for the shape. We're using theorem-proving techniques for reasoning about the content. But we also believe that there's interplay between these two reasoning activities. So we're currently adapting our existing and extending our existing proof plans for our use within separation logic. This is within the Isoplanar proof planner, which is developed at Edinburgh University and which fits onto the Isabelle proof development environment. That's our proof checker here. We're building, as I've said, upon the off-the-shelf shape analysis tools from Peter O'Hearn's group and also the Cambridge group. And our hypothesis of the overall project is that the proposed cooperation will increase proof automation and thus promote more comprehensive level of specification. So up until now, people have been focusing on shape properties. We believe that we can bring content into those and extend those shape properties to have more comprehensive specifications. and therefore more comprehensive guarantees. Okay, thank you. Questions?
So I just wonder whether you have experiences how easy it is for freshmen to get acquainted to this approach. So how long do I need to train some guy until he's able to do a proof with this?
Okay, so what we're aiming for is automatic proof. Okay, so the inputs are the program, the precondition, and the postcondition. So that's one question that we're not addressing. We're assuming that we've got a contract, a specification to work with. We're not assuming, well, our research strategy is to go for full automation. Okay, so obviously in general that's undecidable, but we'll see how far we go. But it's a good point you're raising. So one of the outcomes from this, you could imagine, is a tool which will give you suggestions as to what a loop invariant should be and invite the user to instantiate parts of the loop invariant of a frame axiom, for example. So we wouldn't expect people to do low-level proof. We would typically be, in some of our previous work with this proof critic mechanism, we developed an interactive version. So basically, you didn't know anything about the proof until things went wrong. And then the proof system started to have a dialogue with the user. It presented lemma schemas, and it also presented a candidate instantiation. So the user could select that lemma or generalization, or they could choose to instantiate the lemma, which was partially instantiated, to fully instantiate it themselves. So what we would believe is that we would raise the level at which we could interface, or rather people could interface with a proof development environment.
Do you have any sense of what percentage of the theorems that you want to prove are provable automatically right now? I remember hearing numbers from way back when Abrial was working on the B method of something like 90% or whatever, and it seemed like Colin this morning was talking about numbers like that as well. Do you have any sense of that? And is the remainder these things like inductive proofs and discovering invariants and things like that?
Okay, so that's a good question. So we don't have a real feel for it yet. In our previous work with Spark, so the Spark toolset didn't address the problem of loop invariant discovery. So typically safety-critical software doesn't have many loops, and they're usually fairly simple loops. So, but we were able to increase, basically, we got 80% of the loops that we encountered in the case study data we were given to by Praxis, access to. But we don't really know how far we're going to go with this. So obviously one set of data is going to be to look at just the literature around separation logic, where people are doing proofs by hand and interactively and show that these techniques can be used to automate in that area. But we're also talking to industry. So in terms of the grand challenge for verified software, one part of that is to develop links with industry. And there's people in the UK we're talking to where we can get access to real case studies. So there, we're not going to be too ambitious, but we will be focusing on maybe key areas of, say, runtime operating systems. Things like that is the kind of area we're thinking about, where you have a scheduler involving queues, and we could maybe verify certain functional safety properties, that the ordering of priorities in the queue are maintained over time. We feel we could get those kinds of examples. So, thank you again.